If you clicked on this video, you know that integration by parts can become quite annoying. Often, finding u is only half the pain. The worst part is performing integration by parts over and over again just to solve one integral. Yes, it can be very frustrating. But fear not, there's an extremely useful technique that solves this problem for us, the DI method. D stands for differentiate and I stands for integrate. So when we set up a table with a D column and an I column, you can probably guess what's going to happen. Just like the start to any integration by parts problem, we must pick the function that we are differentiating. That's the u. That's the function that goes in the D column. And the function that's left is the one that we'll be integrating. That's dv. The next term in the D column is the derivative of the previous term. The derivative of x squared can be found using the power rule, 2x. Now for the I column, we find the antiderivative of the previous term. The integral of cosine of x dx is sine of x. With that, we filled out the first two rows of the table. Now for the rest, let's first focus on finishing the D column because that will tell us when to stop adding rows. To find the derivative of 2x, we can use the power rule, which gives us 2, and the derivative of any constant is 0. Whenever we see a 0 in the D column, that's our sign to stop. Now, we should also stop if something else happens in the D column, but we'll talk about that later in the video. For now, we just filled out the D column. To complete the table, we just need to finish the I column. The antiderivative of sine of x is negative cosine of x, and the negative antiderivative of cosine of x is negative sine of x. Awesome, the table is done. Time for the fun part, multiplying. Starting with the first term in the D column, we multiply each term diagonally with the corresponding I term. So for x squared, we ignore the cosine of x and multiply it by the sine of x. Similarly, we multiply 2x by negative cosine of x, and we multiply 2 by negative sine of x. The last term is 0, so we can stop here. Now we're very close to the answer. Before we combine our terms together, we need to apply alternating signs. We start with a plus, and then we have a minus, and since this term had a minus, the two negatives will make a positive. And finally, we have another positive, which is multiplied by a negative, so that just becomes negative. Awesome. Once we combine these three terms together and add an arbitrary constant to the end, we have the solution to our integral. The DI method reduced this integration into a cakewalk. The great thing is it works for any integration by part integral. The first step is to find the u that produces the simplest outcome. To do this, we can follow the LIATE guideline. We have an algebraic function and an exponential function. So according to LIATE, we should use x cubed as u. So we'll put x cubed in the D column and e to the power of 2x in the I column. Alright, let's knock out the D column first. To find the derivative of x to the power of 3, we can use the power rule, which gives us 3x squared. And now for the derivative of 3x squared, we can use the power rule again, giving us 6x. And taking the derivative of 6x, we get 6. And the derivative of 6 is 0. The derivatives are complete. For the I column, we start with the antiderivative of e to the power of 2x. Now, to integrate this, we can use some U-Substitution. If we set u to 2x, then du is 2dx. That means dx is 1/2 of du. If we substitute in u and 1/2 du, this integral becomes a lot simpler because we know the integral of 1/2 e to the power of u du is 1/2 e to the power of u. And of course, u is 2x. So the antiderivative of e to the power of 2x is 1/2 e to the power of 2x. Now, for the integral of this term, it's basically the same as before, except we're multiplying it by 1/2. So the antiderivative of 1/2 e to the power of 2x is 1/4 e to the power of 2x. And for the antiderivative of 1/4 e to the power of 2x, we're just multiplying the antiderivative of e to the power of 2x by 1/4. This gives us 1/8 e to the power of 2x. And then for the antiderivative of this term, we're just multiplying by 1/8, which yields 1/16 e to the power of 2x. Our table is done. Now we want to multiply diagonally. We have 1/2 x to the power of 3 e to the power of 2x. And then we have 3/4 times x squared times e to the power of 2x. Following that, we have 6/8, or 3/4 times x times e to the power of 2x. And finally, we have 6/16, which is 3/8 times e to the power of 2x. Nothing is left in the d column, and we have all of our products. Now, we have to give each term alternating signs. And finally, we group all the terms together, slap an arbitrary constant to the end, and admire our work because it's correct. Okay, now let me show you an instance where we must perform the DI method a bit differently. You'll see the problem in a second, but like the start to any integration by parts problem, we must first pinpoint our function for u. LIATE tells us that we have a trig function and an exponential. So we'll make the trigonometric function, cosine of x, our u, meaning e to the x will serve as dv. In the context of the DI method, this means that cosine of x will fall in the d column, whereas e to the x will be placed in the I column. Can you see the issue yet? To fill out the d column before, we took the derivative of the previous term until we hit 0. But notice what happens to our d column with cosine of x as our lead term. There will never be a 0 in the d column, at least not with these functions. So instead of searching vainly for 0, instead let's look for a multiple of the starting term. Whenever we spot one, we can stop adding rows. Just to clarify here, negative cosine of x is a multiple of cosine of x, so these 3 rows are all we need. That's the d column, and now we just need to fill out the I column. And our I column is simple to fill out since the antiderivative of e to the x is e to the x. Fantastic. Our table is done. Now, to get our terms, we start by multiplying diagonally. Cosine of x times e to the power of x, and negative sine of x times e to the power of x. But for the final term in the d column, it's not 0. So instead of ignoring it altogether, we first multiply it horizontally with the adjacent I term, e to the x. And then we take the integral of this. Now, like before, we apply alternating signs starting with a plus. The second term has 2 negatives, so that will become a positive. And with that simplified, we can combine all of these terms together to establish an equation. Now, notice that the 2 integrals are the same. That's not a coincidence. Using some basic algebra, we can move the integral from the right to the left with some addition. And to get rid of the 2 on the left, we just need to divide both sides by 2. And finally, to include all the possible solutions to this indefinite integral, we need to add an arbitrary constant to the end. That completes our answer. Okay, time for a quick recap. The DI method consists of a table with 2 columns, where the D column takes the derivative of the function u repeatedly until there's a 0. The I column follows in its footsteps, repeatedly integrating instead. The solution to the integral is then found by multiplying each term diagonally, starting with the first d term, and then adding alternating signs. The terms are then combined, yielding the desired output. In the case where 0 is not present in the d column, we stop when we locate a multiple of the first d term. We then complete the table and multiply each term diagonally, except for the last term, which we then multiply horizontally and integrate. After applying alternating signs, the solution to the integral can be solved using a bit of algebra and a little bit of brainpower. And that's the DI method. If you found this video helpful, be sure to subscribe. These videos are a lot of fun to make, but they also take up a decent amount of time. So if you enjoy watching these, or if they've been helping you in any way, be sure to hit that thumbs up button and share this with friends. Thank you so much for watching.